right, so let's do that today. So today we're going to talk about the heart. When we finish today, we can explain where the heart's located, how it is protected, it better be protected. We look at the 4 chambers of the heart, the internal structure of the heart. We also look at the blood vessels that attach to the heart. And we look at how the heart is a 2 pumps in 1 situation. And how it pumps the blood through the lungs and then through the rest of the body. Pulmonary means lungs. You see the word pulmonary? That means lungs. We talk about the flow of the heart, the flow of the blood through the heart. The blood flows in one direction. It doesn't flow back, it just flows one way, so we can go step by step by step, so that's okay. We'll have a little discussion about heart valves. And then we go into the electricity of the heart, how the heart gets triggered to contract. Because a heart contracts like 60 to 100 times a minute or more. And it's got to be pretty coordinated how it does that. So we'll talk about the electrocardiogram as well. And then we get into the contraction relaxation. You might have heard the term systole and diastole before. Systole is when the heart contracts, diastole is when the heart relaxes. So we take a blood pressure, we take two numbers, a higher number and a lower number. That responds to those two, the contraction and the relaxation. And then make sure we do a little bit of math in here also. So we have a formula of how to measure how much blood does a heart pump in 1 minute. And lastly here, the heart supplies itself with blood. We'll have to look at that anatomy too a little bit. Good. So where's the heart located? It's positioned in the chest between the vertebral column in the back, the spine in the back, the bones posteriorly, and the sternum, the chest plate in the front, anteriorly. Laterally, it's protected by the lungs on the outside. So you see that here. The lungs are like cushions for it. On the bottom side, we have the diaphragm, the muscle that separates the whole thoracic to the abdominal cavity. And I always think of that like the thoracic cavity is mostly air. And the abdominal cavity, there's no air, it's all liquids and solid stuff. And so up here, we kind of breathe up and down, down also is the diaphragm. And so that the air goes in and out. And down here, we have that core. We talked about the core, where we can compress that liquid and then it's really nice and solid and sturdy. So that's one of the differences between the thoracic and the abdominal pelvic cavity for me. The apex of the heart is touching the front of the chest wall at an angle. So when you look at the heart, it sort of lays in the body like that. So the bottom part here is known as the apex, and it sort of goes forward, angling down a little bit. So it goes towards the chest wall. And the base of the heart, that's the top portion of the heart. You can sort of visualize it's a little bit of a triangle here. Its tip is at the bottom and the top is much more broad. And so that's called the apex because of that, and the base is on top. And that is more on superior, posterior, and the base is where the great vessels come out. So these here that you can see here, this red stuff and this blue stuff here, those are called the great vessels. There are these things up here that sort of, you can almost visualize that the heart is hanging down on those and it's sort of suspended in the chest. Don't you like I start underlining things? I know it makes it easy for me to teach it. But of course that was the afterthought. It was more like, how can I make it as easy for you guys as possible? Because this is a very interesting concept. It's brilliant, but it's a little complicated to understand. Protection of the heart. The heart is protected in this fashion, but also the lungs and a lot of the abdominal viscera, the abdominal organs, are also protected in this fashion, with this sort of membrane system. And that membrane system is known as the serous membrane system. And what happens in that system is organs are suspended within two membranes, or that whole membrane system. Like, we take a fist and push it into a balloon. And so what we're going to get created an enclosed space between the serous membranes attaching to the organ. So what we're going to get is we have when we put a fist to the balloon, we have one part of the balloon that's on the outside, and then another part of the balloon is sort of like right on the fist on the inside. And so if you actually were to take, you were to just cut through here, of course it will pop. But if you take the heart, you can cut through here, or you could cut through here, and you end up having something that looks like it's two membranes. Because you don't know that there's one balloon. You don't know it's one thing. And so it has a membrane that's on the organ, on the fist, or the heart here, and then a membrane that's towards the outside, towards the wall. But it's not two membranes, it's one membrane that is connected on top, on one side, and then on the other side also. And so we're going to create a space on the inside that's enclosed. There's no connection to the outside with what's going on inside of here. And so inside of here we can secrete some fluid. So we got a little bit of liquid, like water, but a little bit more oily than water. So it's a little glitchy. And so when the heart pumps and it moves and it contracts, it can move inside that liquid, and it's sort of like left alone by that. It doesn't have to be pushing everywhere and all over the place. And so that's that system. It's really, really brilliant. And so organs are suspended within the serous membranes, as if we push a fist into a balloon, creating an enclosed space between them, the serous membranes. So that's that in between here. And one part of the membrane is attached to the organ, and we call that the visceral part of the membrane, the visceral layer. When you see that word viscera, you're always thinking internal organ type of stuff. When you think internal organs, you're thinking heart, lungs, gut, that kind of stuff. You don't think muscle and bones. And you don't think brain. You're thinking gut, chest and gut stuff. So whenever you see viscera, you have something to do with those organs. So the membrane portion that's right around that organ is called the visceral layer of that membrane. And then the one that's on the outside, that's attached to the cavity, I should have taken the other color, huh? That's known as the parietal layer. Parietal means on the outside, the parietal bone in the skull. That's the outside bone. So that means the wall part. So this is really cool because, well, we have epithelial cells. Remember epithelial cells, they do stuff. Yes?
So open heart surgery, do they have to cut through that membrane?
Yeah. It gets complicated. I know. I mean, it's still, open, heart, they know the heart real well. They're incredible with the heart. Like compared to other organs, the brain, the heart's like quite simple that way in respect to understanding how the mechanics work and how, but still, it's incredible. So they are incredible with hearts. Especially when you look like children's stuff, it's amazing. Those small little things. So we have these epithelial cells, they secrete fluid. They secrete that serous fluid, they call it the serous fluid, that fluid that's inside the space. And so what that fluid does, it helps reduce friction during movement, and that's good. What it also does, though, is really cool in the lungs. It suctions the lungs to the chest wall. We're going to talk about that when we talk about respiration. That's really fantastic. Because lungs are like fluffy, puffy teeth. They're like, air sacs. They can't just inflate and deflate on their own. There are no muscles. There are no so what happens is the lungs are attached to the chest wall and to the diaphragm through this system because we can create a suction of this membrane to this membrane in the lung. And when the chest wall moves and the diaphragm moves down, the lungs follow it. They get pulled with it. And that creates a suction through the mouth and through the nose, and that's inhalation, and then exhalation when we push it back out. So that's really neat. And then the last thing we want to talk here is the name of these membranes. So we have the inner layer is known as the visceral layer, the outer layer is known as the parietal layer. And then it depends on which organs are they in. So that the heart stuff, we call that pericardium. Peri means around. Oops. Peri means around, and cardium means heart. It's a membrane around the heart. In the chest, it's known as the pleura. Maybe you heard before somebody having pleurisy. Ooh, how do you spell that? I think this way. Pleurisy? Probably not quite this way. Maybe this way. But anyway, that's an inflammation of this membrane in the lungs. And you can only imagine if this fluid in here is not really secreted, and in the lungs this fluid is supposed to reduce friction. There's movement here, a lot of movement, and suction it. So you got a dysfunction in both of those. That must hurt like crazy when you try to inhale, if there's no fluid in here, there's not much fluid in it. So that's, yeah, when you look at the pathology, you're always looking at the names. You're always trying to figure out, what would that name mean? Like when you see a thing called an itis, you know it's an inflammation. Whatever itis is an inflammation of that thing. All right, so that's the protection linings around the lungs and around the heart, of course, because we're talking about the heart right now. So the heart's enclosed in the pericardial sac, and the outer layer of that sac is known as the fibrous pericardium. Watch out, this visceral parietal stuff is coming right back here too. So the fibrous pericardium is right here on the outside. Well, that doesn't work no more. It's right here on the outside. That doesn't work no more either, huh? Okay, let's do that again. The fibrous pericardium is right here on the outside, and it anchors, it's dense connective tissue. I wrote that down in here. So it anchors the heart to its surroundings. And then we have a second layer to that pericardial, to that heart wall, the pericardial sac. That inner layer, and that inner layer becomes the parietal pericardium. And then here you see how it connects. Because the next layer on the inside will then be the visceral pericardium, right here. And the visceral pericardium is also known as the epicardium. I know, Jesus, can't they keep their names straight? But you just got to slow down with the names, because even though there's a lot of these names, but at least you got them all on one page, so you can always look them up. Epi means around, on top of something. So epicardium is the membrane on top of the heart, as a word. So epi, we'll say epi means on top. Peri means around. So that's the bigger envelope on top, around the whole thing. A pericardium. But see, the cardium comes back over and over. And then, you heard before, right? The heart is a muscle, a heart muscle. We talked a little bit about that. Not that much. And the heart muscle, the name for that is myocardium. That's the red stuff here. That's the red stuff. And remember the word myo? What does myo refer to? Muscle tissue. That was in the chapter when we started muscle. Myo, sarco, mysio, all that. Those are muscle terms. So myocardium means heart muscle. See, if they would have written it in English, then we go to China, we got to learn a whole different word. But this time we can just go around the whole world. It's always the same word. It's perfect. And they probably try to write it in English too, so we can read it even. And then on the inside, we have one more membrane that lines the inside of the heart chambers, and that's known as the endocardium. And endo means inside. Yeah, you almost want to have like flashcards with these namey things. Because the prefixes, they go back over and over, and the suffixes too. And so a lot of it is just putting names together. So we have the visceral pericardium in the heart itself is the epicardium, that's right here. Then beneath them is the myocardium, that's that muscle, which is the actual muscle of the heart. When it contracts, blood gets pumped through its chambers into vessels that deliver it to all the body cells. If the myocardium is starved of oxygen or gets damaged, we have a heart attack, or that's also known as a myocardial infarction, an MI. That's a very bigger problem we have in our world, in the Western world generally. The endocardium lines the heart chamber themselves and is continuous with the inner lining of the blood vessels. And we're going to talk about blood vessels like way after the break when you remember nothing about this. But I hope you forget this whole thing a little bit. You go and have fun, we can go back and then do it again, right? But inside the blood vessels, they don't call it endocardium. They also don't call it endoblood vessels. They call it endothelium. Thelium. Endothelium. This is all prep for the brain, you know. Just kidding. Then we have blood vessels. Yeah, we have a lot of. So the heart, you know, the cardiovascular system is a heart that pumps the blood, and it pumps the blood through all these vessels in the body, and then it delivers liquid things to the tissues and the gas like oxygen. That's the main thing: oxygen, glucose, and of course a lot of smaller things. And then it takes the waste and brings it back and delivers it to the organs that can excrete it. The lungs for this carbon dioxide, etc., etc. The kidneys, and then also the digestive system. Well, the kidneys in terms of the blood. Arteries are, have you heard of the word arteries? Yeah, so arteries are vessels that attach, no, they don't all attach to the heart, but they are vessels that carry the blood away from the heart. So all the blood travels through the body in one direction, or it travels through the vessels in one direction. So arteries are vessels that carry the blood away from the heart. Veins are vessels that carry the blood, that guide the blood from the body back to the heart. So those are veins, the blue ones. My blue doesn't work anymore. No, not that much better. And so now we have vessels that go from the heart. We have vessels that go to the heart. And then we got vessels in between that connect to the arteries of the veins. And those are capillaries. Capillaries are between them throughout the body. They are leaky, so that blood seeps into tissues to exchange substances like oxygen and nutrients. So arteries and veins are not leaking blood out from within them into the tissue. They're just channels, they're freeways. But we need the oxygen to go to the cells of the tissue, otherwise it's not going to do any good. Same with the nutrients. If the glucose doesn't get to the muscle cell, it's not going to do any ATP. It's not going to make energy. And so for that we have capillaries, and capillaries, because of that, are leaky. So they seep, the fluid from the inside of these capillaries seeps into the tissues on the artery side, and then on the venous side it pulls it back into the system. Also, the lymphatics. If you have lymphatic stuff, if you heard of lymphatics, lymphatic drainage or so, that's also that's helping this system. We want to talk about that on Monday in a long time. Oh, well, there we go. So those are the main three types of vessels that we're gonna study We're not going to do too many naming ones because we just came from naming all these muscles and we're a little named out in that respect, so we're going to leave that to the next class, but I want to just give you the general concept of how the blood vessels work. And a lot of the names of blood vessels are like where they go through, like brachial, subclavian, and the ulnar and the radial. We already learned a lot of those names, and you will make up where they are when you learn identifying them. When we open a heart up on the inside, now you can open your heart up. I mean the one on your table. I hope the other one's not too close to start with. Inside the heart we have 4 chambers. We have 2 chambers on top and we have 2 chambers on the bottom. The top chambers are known as the atrium. So we have the heart's like that in the body. So the right side, when you look at me, that's your left, that's the left side for you. But it's the way we look at anatomy is we're looking at from the perspective of the patient. So no matter what part you're looking, no matter which direction you're looking at the heart, this is always going to be the right side of the heart. Because in the patient, it's going to lay like that. It's not going to turn around inside the patient. Hopefully not. So the top 2 chambers are atrium. The bottom 2 chambers are ventricles. The top are the 4 chambers. Atrium means 4 chamber, or receiving chamber. Well, it's a 4 hall in a building, it's the atrium. And then a ventricle is also known as an ejection chamber. Because when we squeeze this one, that's when the blood travels through the body. The atria are the chambers where the blood comes in, sort of trickles in. And then the ventricles is when it contracts and the blood gets pumped either to the lungs or to the rest of the body. And when it goes to the lungs, we know that as the pulmonary circuit. Whenever you see the word pulmonary, you're thinking lungs. And then, and that happens actually, that blood comes from the right side here. That goes up into that goes into the lungs here. That goes to the lungs. 2 lungs. And then, on the other side, we have, well, when the blood then comes back from the lungs back to the other side of the heart, the other side pumps the blood to the whole body, the whole system. So they call that the systemic circuit. So when the blood gets pumped actually through here, that goes to the body. So that's the systemic circuit. Systemic. Blah, blah, blah. So that goes through here. Yes? And the left ventricle pumps blood. It goes behind this part here. It goes behind here. It pumps blood to the body. That includes the brain, the arms, the everything else other than the lungs. It actually also includes, well, no. No, it does. It includes the lungs too in terms of feeding the lung tissue. But it doesn't feed, it does, the pulmonary circuit is here so the blood can pick up oxygen from the lungs. So that's what that is. I know, it's getting more complex, huh? Pulmonary circuit, systemic circuit, atria, ventricles. Yes. Yeah, that's, well, you know, we're going to have this main vessel that goes actually from here, and then it goes down through the abdomen, and other vessels come off of it, and they feed the different organs. And then at the end, it goes into the legs. And then from there it comes back with veins. So the arteries go out and the veins come back in. Mm-hmm. Between the right and the left part of the heart, we have a wall, a heart wall, and they call that a septum. a muscular part, and so it's a muscle that it's muscular that separates the left from the right side. So the right atrium and the left atrium are divided by interatrial septum, they call that. The septum means wall. And the ventricles are divided by an interventricular septum. Septum is a wall between, so we have this bottom part of the heart and the top part of the heart, right? So when you actually look at, it's interesting, when you look at the heart, let me see if I find the skeleton. The skeleton. I don't think I have a picture of the skeleton, but if you kind of see here, this thing around here, this here on top is the atrial area and below is the ventricular area. So the heart you can sort of divide between the top and the bottom, and there's like a lot of tissue that's the white tissue in the muscle, that's the fascia, that sits in this plane and encircles it like a crown almost, like it goes around it. And it's almost like a skeleton, but it's fascia, it's not bone, but it makes it sturdy. And so in that plane, you have then, from there, you have the top part of the heart and the bottom part of the heart. And then you're also needing to have a connection, a separation between the left and the right part of the heart. And that's done by a septum. They call it the septum, it's a wall, they just use that term. And on top where we have that between the two atria, we call it interatrial, in between is interatrial septum, and where it's between the ventricles, we call it interventricular septum. Inter means in between. So septum is wall. Interatrial, interventricular. Yeah, again, a lot of this is terminology, just hearing about this a few times and it starts to roll more off the tongue because it's word creations. You know, it's playing Legos with words. So then that brings me to the topic of heart valves. And the heart has two sets of two valves that guard both the entrance and the exit of both ventricles to prevent backflow. So I said the blood travels in one direction. So the blood from the systemic circuit comes up from the body, comes from below and above the body and enters into the right atrium here. And from there that blood will flow down into the right ventricle. And then from there the blood goes into what we're going to learn as the pulmonary trunk. Again, pulmonary means lungs. So when you read pulmonary, you're thinking it's going to the lungs or coming from the lungs. And so and that flow of blood, some of that is gravity, like the way that the blood goes from the atrium to the ventricle, some of that is gravity. But you're not going to have gravity eject that blood outside of the ventricles. And so when a ventricle contracts here, that blood has two holes it can go through. It can go either one way to the pulmonary trunk, or it can go back to the atrium on the right side. But would that make sense? That's where the blood came from. We don't want it to go backwards, we want it to go forward. And so now what we have here a valve. And you see this valve on your model here, or if you don't have it, you go look here, but the valve here is right here, that white stuff is symbolizing that valve. And that valve is known as the atrial ventricular valve because it lies between the atrium and the ventricle. And when the heart muscle contracts, that valve closes up and closes this here and makes a door that shuts, that the blood cannot go backwards. It cannot go backwards because of that valve when it's closed. And this valve is very interesting. The valve is oh, you can see that actually in here. The valve, this is one of those valves between the atrium and the ventricle, and it has some tendons like these little strings on it. They call them heartstrings, or chorda tendineae. I know. Tendinous cords. And then from there, from the chorda tendineae, those cords anchor into a little muscle thing known as the papillary muscle, right here. Papillary muscle, I think the label is lower down. Here, papillary muscle. And then below that, we have meaty parts of the muscle, which also have a purpose in the heart, but we're not going to talk about that right now. But when the heart muscle contracts down here, when a muscle contracts, it shortens. So the heart muscle contracting, it will shorten this whole heart a little bit. And then these tendons, they don't shorten. So these flaps get pushed up a little bit into a place where they're closing this hole between the ventricle and the atrium. So you can think it's kind of like a sail that's attached to a string, and the wind pushes it and you want to let it go, and you don't want to let it go too much, so you have that tension. It's like that. And we want to keep these flaps, these wide flappy things here, these leaves, they call them actually. We want to keep them in a place between the atrium and the ventricle, between the ventricle and the atrium, so we do not have any backflow of blood when the heart contracts. But that's one set. Man, that was a little bit of a hard explanation, wasn't it? You understand that a little bit? Yeah? Good. Because then we got the other sets of valves. And the other sets of valves are known as the semilunar valves. And that's, the semilunar means half moon. And when you look up from the heart, these valves are these valves here. So this is actually a shot where you're looking from the atria basically downward into the ventricle. So you cut the top of the heart off and you're looking down. So you're seeing these are the atrioventricular valves. Sometimes they call them AV valves also. Atrioventricular valves. Or, since these are anatomists and they have nothing else to do other than naming things, to brief us a little bit more, the one on the right side they call tricuspid valve, and the one on the left side they call mitral, or even a different name, bicuspid valve. The reason why they call them cuspid, tri and bicuspid, a cusp is one of those leaves, that one of those flaps that you can sort of see that flaps down and then is attached to the strings. So if you look really, really close, on the right side you have 3 flaps. And on the left side you only have 2 flaps. And so that's why they call the ones where there's 3 flaps tri means 3, and where there's 2 flaps they only call it bi, because bi is 2. Yes?
Can be tricuspid valve, they'll never be bicuspid.
You mean as an anomaly?
Probably.
I don't know. I mean, if you don't have pain, if the hole here either doesn't close fully or is not opening fully, you're going to get turbulence in the blood. You get a murmur. And so I would assume, since the design is sort of for 3 flaps, if you have 2 flaps, you're just going to have murmur. But I don't know if that's a very common occurrence or if that is an occurrence. We'll have to talk to a cardio guy. That's a good question. Then there's one more name, mitral valve. And now you know that this stuff happened in Italy or so, because there's or at least where the Catholic Church is, because the bishop's mitre is like 2 flaps coming together on top. So it's a 2-flap thing. And so that comes from the bishop's mitre, the hat of the bishop. I know. You've got to be Catholic to even care about that part, right? So those are these valves, but then the other one down here, those are the semilunar valves. And the reason why they call them semilunar valves is because to the anatomist with a lot of wine in it, that looks like a half moon, looking down at that. Like a little bit of a half moon. I mean, for us, a half moon looks, something like, I don't know, when the moon is half or so, something like that. But for them, it looks like that. So they call these the semilunar valves. And those are valves that guard, right here, the exit of the ventricles. So those flap open to the upwards, they open upwards. And when the ventricles contract, what happens on the inside, this fluid gets really powerful and strong and wants to go somewhere because this contracts firmly, and it's gonna go where it's opening doors. And it's gonna go through this because it's gonna push this valve open, and the blood will eject into the pulmonary trunk, or here, this is gonna be called the aorta, the one that comes from the left side. So on the model, it's gonna push the blood either through here on the right side, into this vessel, that's the pulmonary trunk, or on the left side, you can see it behind the bishop's flap, where you see those white things on top. That's where we have it going to the aorta. That's this vessel, and then from there it goes through the whole body. The blood goes through the whole body. So as the AV valves hold close to let the blood not go back, the semilunar valves are pushed open for the blood to get through and move forward. And that happens when the heart muscle contracts. And when the heart muscle then relaxes, and you have a little blood that still goes up, gravity will fall back down, and now it doesn't have to fall all the way down to the ventricle again. It will only fall back down to these flaps, and then the blood is held up on these flaps and fills up a little bit. And then that puts a little weight on the flap, so the next time the heart contracts, it has to push hard to force it open, and that force increases the force of the blood pressure getting out of the heart. And that helps partly why we can eject blood then forcefully out of the heart. And so there's dynamics, vascular dynamics, that get created with these valves. But for us, most important is that the semilunar valves are at the exit of the ventricles and are pushed open when the heart is contracting. The one that guards on the right side, that is for the blood that goes to the lungs, we call that the pulmonary semilunar valve or pulmonary valve, and the other one that guards right on the other side, on the left ventricle, that guards to the aorta, we call that the aortic semilunar valve or the aortic valve. All right, so that's for valves. Does that make sense then? Why we got these things? You what? Halfway. What we're gonna do, you can do questions for after the break, but that gives you something to do during the break, right? And then we can touch on it again when we come back. So now let's put it together a little bit. So now we're gonna have this blood flow going through the whole thing. And by the way, we're gonna get heart sounds. Have you heard of your heart making sound yet, ever? Yeah, the heart sounds are when the valves close. So we're gonna get to that. But let's talk a little bit more about the pulmonary and the systemic circuit. So the right side of the heart concerns itself with pumping blood to the lungs, where oxygen is picked up and gaseous waste, which is CO2, is disposed. The oxygenated blood, so that's blood without oxygen. That is blue blood in terms of our blood thing. So in the heart, in these models, it's pretty good. The top stuff is color-coded more or less. So blue means deoxygenated. Red means oxygenated. So you have to be very careful that you think red means artery. No. And blue means veins. No. Most places in the body, yes, but not in the heart. Because in the heart, the definition is always the same definition, but in the heart it makes a difference. When you have the vessel that is deoxygenated blood going from the heart to the lungs, that's still an artery, even if it's blue. And then as we get back, we haven't done that yet, we get back from the lungs, these vessels back here are red because they have oxygen, but these are veins. So we have to be careful with that. We have to keep the definition of arteries and veins in the head. Most places that works. The blue is veins, the red is arteries, but not in the heart. There, blue means, well, blue always means deoxygenated blood, and red means oxygenated blood. Because it looks a little bit more red when we look at it. So deoxygenated blood from the body tissues enters the right atrium. We talked a little bit about that before, so that's right here. The right atrium is right there. Via the superior, oh look, new terms. Via the superior and inferior vena cava. These big vessels here, coming from above and below, getting the blood into the right, no, that's it, the right atrium, those are known as the vena cava, superior, inferior vena cava. On the heart model, they're right here. The inferior is right here, and the superior is right here, bringing blood into this front atrium on the right side, the chamber, and so then the tricuspid valve is open, and lets the blood into the right ventricle. So that's also what we already talked about. So from there, the blood then goes to the right ventricle, and from the right ventricle, when that one contracts, the pulmonary semilunar valve opens and blood is pumped to the lungs through the pulmonary arteries. So let's talk briefly about that. So that's right here. See that here? That coming up, and then it goes to the right, to the left, and then to the right over here. So the vessel that comes right off the heart is known as the pulmonary trunk. Let's write that over here. Pulmonary trunk. And then right after, look at this, it's very short. Right after that short little span, it goes into a right and into a left vessel. It splits. Right here, it splits. It's crossing. And at that point, the one that goes to the left lungs is known as the left pulmonary artery, even though it's blue. That's that weird thing. And the one that pumps blood to the other side is known as, to the right side, is known as the right pulmonary artery. So in the vascular world, in the blood vessel world, we often call something that is a little short stub and then splits right into something else, we call that a trunk. That word is trunk. Okay? It's good I get away with on the lab test, I can call this a pulmonary trunk so you don't have to worry about artery or vein. So it's less confusing because it always gets us with the blue and red. It gets me too. That's why I always have to point it out. In the heart, it's different. All right, so that makes that sense a little bit. And then in the lungs, we're gonna exchange the gases. So we oxygenate the blood. We put oxygen in, we get rid of the gases of the carbon dioxide. And so then we have oxygenated blood return to the back of the heart through the pulmonary veins. And see, look at here, they're coming in right here. The pulmonary veins are coming in right here. 4, 2 on one side, 2 on the other side. The right ones and the left ones. And on the model, you've got to turn the model around now. This is where you turn it around. Well, actually, you don't have to turn it around because you see them right here. There's 2 coming in right here. You see those 2 in the front. Those are the left ones, the left pulmonary veins. Even though they're red, that's the other asterisk. They're red, but they're veins. And on the right, they're coming into the back right here. You see that here. And then from there, they go into the, they go into the left atria. And from the left atria, we're gonna get the blood going into the left ventricle through the mitral valve. Pulmonary veins enter left atrium. The bicuspid valve opens and the blood goes into the left ventricle. From there, then the blood, when the blood pumps out of that left ventricle, it pumps the blood to all the body tissues, delivering oxygen and nutrients to the body. That includes the brain, the arms, the legs, the viscera, everything except picking up oxygen in the lungs. And it brings oxygen and nutrients to those tissues, and it picks up waste products and carbon dioxide from those tissues to then again bring it to the lungs and to the kidneys to filter everything. So when the ventricles contract, the pressure inside, this is important, when the ventricles contract, the pressure inside the ventricles rises and it gets bigger until it's strong enough that the blood pushes the semilunar valves open, and from there then the blood is ejected through in this left side, the aortic semilunar valve into the aortic trunk. So you visualize the heart's down here, and you visualize it has to build up pressure on the inside until it's strong enough to push those valves open, like push the big fat door open. And once it's open, it goes faster because it has this energy that's built up. And it's strong enough to push that blood over the aortic arch. That's the aortic arch. You can see that right here. And from the aortic arch, the aortic arch goes down, and basically here, actually this first part we call it the ascending aorta, then we call it the arch of the aorta, and then this is the descending aorta, technically speaking. I know. And then further down is the thoracic, and then it goes down below the diaphragm, it's not the abdominal aorta. But you see that word aorta, you're thinking of that big thing going around. But we will have these first three stops that come off the aorta. You see them right here, boom, boom, boom. So this here is another trunk. You have to memorize these. The first is known as the brachiocephalic. Oh, look, and then they messed me up with my system. See, they're not consistent, huh? See here, they call it the brachiocephalic artery. It's also known as the trunk. They get away with it because there is no other brachiocephalic artery on the right or on the left. There's just one. Because brachio, you remember the word brachio? What does that mean? Upper arm stuff, right? Cephalic means head. So this brachiocephalic brings blood to the arm and the head. That's how you read that stuff. See, a lot of it is slowing down the reading or the listening to it. So the brachiocephalic trunk is very short, and you can only see that here, but here you can see how it then splits into a right subclavian and a right common carotid artery. Subclavian. Have you heard of that word clavian? Clavicle. Clavicle. Collarbone. Sub means below. Submarine. Below the water. So subclavian artery is right below the clavicle. Huh. And then once it goes into the armpit, they call it axillary artery. And then it goes to the upper arm, they call it brachial artery. That's where all that first chapter stuff comes back. The common carotid is the one that goes into the brain and face, on the head stump. So that's the first stump here coming off of the aorta. It's an important stump because that's delivering your blood to the brain. We definitely want that open and working. And then the second stop is the left common carotid artery. And the third stop is the left subclavian artery. Which basically tells you on the right side, you've got first a little stump and then it splits into subclavian and carotid. On the left side, you just come up right from the arch into the head and then into the arm. And it makes sense that the last one goes to the arm and the second one goes to the head. Otherwise, you're going to cross them over. So whenever you think that, most of the body stuff is quite efficient the way we're doing it. It's layered. It's not, when we get to the brain, we learn about that. We have different brains, so to speak. And they have to do with evolution, but it's usually quite efficient. All right, so that's that. Does that make sense? First time around a little bit? Mostly memorizing. Ooh, I gotta get finished here. I'm talking way too long. Oh, look, this is a picture that you can study all this with. Look at how pretty it is. You see all the chordateninae, you see the three flaps here. You see the sort of two flaps here, etc., etc. And that brings me to the coronary vessels. The heart muscle itself needs blood to supply its own function. And the coronary arteries come out of the aorta at the base. You can see that right here and right here. It's a nice picture. And from there, that's nicely oxygenated blood, from there, they go and feed the heart muscle itself. We have a right coronary artery known as the RCA, that's not a TV, and that feeds the right ventricle and the majority of the heart's posterior. The posterior descending branch comes off, with descending means it goes down. On the left side, we have the left coronary artery, the LCA. They like abbreviations, as you can tell, huh? And that feeds the front of the heart. It divides into a left circumflex and an anterior descending interventricular branch. Whoa. Well, I'm going to go through that because that one is on the test. So on the right side, you can see it how it comes right out of here. That's where it comes out. So that's kind of nice to see that. So we want to know that's the right coronary artery. And then on the left side, you cannot see where it comes out of the aorta. It's behind it, but you can see a little stumpy coming out of here, and then it splits right there, right in two. The one going straight down is the interventricular artery, the anterior interventricular artery, because it goes right on the interventricular septum. That's the septum between the two ventricles. Interventricular septum, interventricular artery. Same name. And the other one that goes around, sort of in between the ventricle and the atria, is known as the circumflex because it goes around. That's the circles around. Circumflex, circles around. So there we go. That's these. And then, well, we also have, of course, veins. So the heart muscle gets fed, and then when it's, the blood is finished up, it has to come back, and it comes back through veins. Most of the veins have similar names. The one thing I want to point out is in the back here of the heart, I got to take it off. In the back here of the heart, you see how this is a little bit of a bulging vein. It's a little bit of a bigger vein. They call that a sinus. So when this like a sinus in the skull, it's a little chamber where blood can pool in a little bit or come together. And here it's called the coronary sinus. And it collects the blood a little bit and then it dumps it into the right atrium, which is kind of, that's where the blood comes in from the rest of the body, so the vena cava as well. And then from there, the blood gets cycled, goes to the lungs, gets oxygenated, and yada yada, we go back around. Over and over and over for a long time. Good. How many more I got? Well, the next thing now we have to talk about, how does the heart muscle contract? And the heart muscle is kind of interesting. It has its own source of impulse production, initiating then a muscle contraction. So it has its own nervous system. So on top here, right there-ish, it has what's known as a sinoatrial node, an SA node. And that's interesting. Those are like cells, muscle cells, that leak calcium, and when they leak enough, it fires a nerve impulse off. Like your leaky cells are responsible that you're firing a nerve impulse. Yes, ma'am.
Is there sinoatrial like electricity or
The who?
is there like electricity?
Yeah, that's the electricity. Yeah, when we're talking about nerve impulse, we're talking about electricity. We're going to actually have a whole chapter. That's a good question. It's a little ahead of myself. Yeah, because when you talk about muscles, you've got to have the muscles need to be initiated or irritated by something, then it contracts, and that's a nerve. And so the heart muscle is just a regular muscle from that perspective, so it has to be told to contract. It's not just going to do that, and we do that through the electrical impulse. And so most of that comes from the brain for the body, but the heart is unique in its own, that it has its own nervous system that way, and its own impulse creation. And it does that about 60 to 70 times per minute as an impulse. So 60 to 70 times per minute, we're going to get a discharge of a nerve impulse from this end here, from the SA node, and it sends that impulse through up here, through the atria, but it also sends it down here towards the ventricles. And right there in the wall of between the atria and the ventricles, we got to have another node, another cluster of cells that are like discharging impulses also. It's known as the AV, atrioventricular node. And so that's around Oh, actually, you know what? I made a mistake here. Sorry about that. The SA node is on top here. Sorry, that's on top here. So the impulse goes through the atrium, and then this is actually the AV node in the plane, like right in here. And then when that gets stimulated, it enforces the impulse, so it gets stronger, and it goes down in between through the interventricular septum and around the ventricle, and all together that ventricle that will be fed with an impulse and contracts all at once as a unit. So that's pretty neat. So the names for these things are sinoatrial node, AV node, atrioventricular node, and then as we get from the AV node, we have a thing called the bundle of His that carries the impulse through the fiber skeleton, and then as it gets down into the interventricular septum, we call those the right and left bundle branches coming down here. And as they go around, they then change a name. For some reason, they change a name, and they call them Purkinje fibers. I need you to remember all of those names, but it's good to have them somewhere when you come back and you want to know, because somebody says in a report, well, at the level of the Purkinje fibers, the thing didn't spread. And you're like, what the heck is that? And you can look it up. I never had to look it up, but I'm just saying, just in case. But those are those namey things for that. So that's the anatomy of the conduction system of the heart. The way that this conduction system works with the SA node going first, it actually contracts the atria a little bit, and a little bit before the ventricle contracts. So that's kind of cool, because now you can have blood coming in to the ventricles, sickering slowly in, going to the atria going then to the ventricles, and at some point the top contracts slightly to push it a little more into it, to push the blood a little bit more to the ventricles. And then that stimulation goes over the ventricles, and a little delayed, then the ventricles will contract. And then they send all the blood through the body or through the lungs. The cardiac cells, they are actually it's not just one muscle, the whole heart. It is many muscles put together. And what they are though, they are having junctions. Remember that when we talked about junctions in the epithelial tissue, the desmosomes and the tight junctions, the watertight ones, and then the gap junctions. And I said that's going to come in a heart muscle. And so the gap junctions are like little channels between one heart muscle and the next heart muscle, and they let ions go through them, and so they let a stimulus, an impulse, a nerve impulse go straight through them. So that's why the heart, all the cells together can contract as one unit, and they don't all contract individually. They don't all have to have a nerve going to them and stimulating them, not like a skeletal muscle has to. And so they call that, when they contract together as a unit, they call that a functional syncytium. So that's, functionally speaking, they work as one unit, even though there are many different cells that are attached to one another. So that's kind of interesting. And then, of course, the frequency and the force of the heart muscle contraction can be influenced by the brain. That's why, all of a sudden the heart starts pumping for no friggin' reason, you're thinking, and it's going all fast, and then later on you realize why that was the case. The brain influences that. Okay, the intrinsic nervous system of the heart does not understand if we're doing exercise, if we're upset, if we're anxious, if we're happy. It does not respond to that. And it's very interesting. I have one patient, she's a neuroscientist from Russia, and she had, her heart started being arrhythmic, and so at some point you had to have a pacemaker. And she really felt sluggish. She's like, I can't do anything, I don't care about the world, blah, blah, blah. And then after the heart was sort of set right and fine-tuned, they have to fine-tune that stuff. It's really interesting. You get hooked up to a computer. Her energy level is all back, and it's like she cares about things. It's not just the energy, it's not just the oxygen, it's also like, the heart's the seat of the soul. She came in one day and she's like, I really understand that now. So that's kind of interesting. So we have to be you know, scientifically we think, oh, everything is in the brain and stuff. Well, maybe not so much. Maybe it's all over the place. We also know when we talk about the gut, we know that the gut has more nerves going to the brain than the brain has to its own self. We'll talk about that some more. So that's also interesting. Why I think the gut feeling is a very important feeling in understanding how the world works is through the gut. Anyway, so far the heart has its own nervous system that generates impulses, but it can be influenced by the brain and the brain stem and also the forehead where we have thinking going on. Good. And then that, look, have you seen this before?
Yeah, I have. I finished medical assisting here, the program, and we have to do an externship. Yeah, that's what it's called. And I got sent to a private practice last summer, and I did a few of them. I couldn't do too many because it's mainly women that came in there because we had a PA that did what's that, obstetrics or something. Yeah, so
Yeah.
I didn't get that much experience on it, but it's like.
Well, it's interesting, right?
Like the
how you have to place them, the leads and all that.
Yeah, the leads, yeah.
Yeah.
They have a paper print of the machine.
Right, and so the paper printout looks like that. And so we have these different wave things that come up. And so this measures electricity going through the muscle. So we have the first little bump here that we see is called the P wave. And the P wave is when the cells discharge, the electrical impulse goes over the atrium. So there's a spread of the excitation, that's a nerve impulse excitation over the atrium. And then we get this big QRS complex, that's right, a QRS complex. And that's when the ventricles get excited. So the electrical spread over the ventricle is much bigger than over the atria. You can see that difference, that little bump here, that big thing here. And then at the end there we have another little bump, and that's known as the T wave. And the T wave is when the ventricles repolarize, when the nerves reset. Repolarize, you can sort of think of a nerve reset. The nerves have to reset a little bit because nerve impulse has to do with ions, with mineral things, ions going from one side of a cell membrane to the other, and so you mess up the chemical mixture, and you have to reestablish that chemical mixture, and that's a reset. So we'll talk about that when we get to the nerve impulse more in detail. But that's your electrocardiogram. So the electricity going over the heart. P wave, QRS complex, and the T wave. And so when the heart contracts, we know that as a systole. When the heart relaxes, we know that as diastole. So the heart is contract, relax, contract, relax, contract, relax. And with that rhythmic contraction, it pushes a little small volume of blood forward every time it contracts. And after it contracts, it has to relax, because if it contracts and the blood gets pushed up and out of it, if it keeps contracting, there's no more refilling going on. So it has to relax so the blood can refill, so we have some blood to then be pumped out of the heart again. So that's very, very important. And the heart valves, we talked about that already. They make sure that the blood just flows in one direction and doesn't flow backwards. That wouldn't be efficient. But when it comes to the heart valves, we have the sounds associated with it. And so the closure of the heart valves makes a sound. And the first sound, the lub, you hear the first sound is a lub sound. That's when the AV valves close, when the ventricles start contracting. And then the second heart sound is the dub sound, lub dub, and that's when the semilunar valves close, when the heart goes into diastole. Lub dub, lub dub, lub dub. And we can listen to them. When we listen to them, we call that auscultation. Listen to the valve closure. It's very important to examine. The sounds are conducted along the bloodstream and are easiest heard where the blood travel closest to the chest. So you can listen to these valves with different parts of the chest, and you hear different valves best, even though they're not right where they are. That's where the sounds project. And so I put a little up here so you can sort of see where they are in case you're learning that in, an MA program or something like that, right? When a heart valve is pathologically distorted and cannot open, we call that stenosis. Cannot open is known as stenosis. Or it cannot close properly, and we call that insufficiency. And that creates blood turbulence because of the heart, and that we call it a heart murmur. So you can sort of understand if it's stenosed or if it's insufficient, because like, is it stenosed, then you have an AV valve that doesn't open, then you get a shh, and then you get the heart sound. Because the heart sound is when it closes. So if it's not opening fully, you get a turbulence, a shush sound before it closes, and the closing is the lub. If the sound, the shushing is after the lub, after it closes, you know it's insufficiently closing because the blood goes back when it shouldn't go back. And so you can slowly then, when you hear things, that's what they do. They record all that stuff, and then they measure it, and it's incredible how much they do in the heart, understand how the heart works through hearing. They have these microscopes, these stethoscopes now that are like, they are like seismic technology picking up all the little things that are happening in there. It's not just the human ear anymore. It's very, very interesting. I did a workshop on that at some point. And that gets me to the cardiac cycle. And so this is a really cool chart, because here you can see everything that you need to know about everything. So, and this is just when you trace the blood around the heart, what happens and where does it go? So we have on each side of the heart, on the right side and on the left side, this happens simultaneously. So the first thing that happens, we have the atria is filling up with blood. The blood goes into the ventricles. At that point, the AV valves are open and the blood flows passively from the atria to the ventricle. And then we get a little contraction of the atria. That's when the SA fires that impulse over the atria. We call it an atrial kick. That's when the atria pushes all the blood it's got into the ventricles, and that accounts for about 20% of the filling. And at that point, then after that, we have a ventricular contraction. The first part is an isovolumetric. Iso means same. Volume means the volume, how many quarts are in there. So isovolumetric means there is no blood leaving the ventricles. The whole blood stays in there. During the early phase of systole, the ventricular myocardium contracts, but the semilunar valves are not yet open. With the AV valves closed, the intraventricular blood pressure rises rapidly until it's strong enough that it can push the semilunar valves open. And at that point, we have ventricular ejection. So then initiated by the opening of the semilunar valves, the ventricular myocardium contracts maximally, ejection about 70 milliliters of blood each time it contracts. And we call that a stroke volume. Each stroke, that's how much we eject. And then after that, we have an isovolumetric relaxation with the myocardium. That's a very brief moment, but with the myocardium relaxing, the intraventricular pressure falls below the arterial pressure, closing the semilunar valves, but the AV valves are still closed briefly before they open, and the heart muscle relaxes enough, and then we go right up back to here and we fill up with blood in the ventricle. So this is how the cycle goes. So on this piece here, up here you see the electrocardiogram. Down here you see the heart sounds. First is lub, second is dub, lub dub. Here you see the pressure inside the heart. You see here the pressure in the atrial, in the left atrium, the pressure in the left ventricle. See, when the ventricle contracts and it doesn't open all that, it goes straight up, and at some point the valves open and then it relax, and then the pressure can escape the ventricle. And then here we see the volume, how much blood is in there. See, it fills up. And when it empties, the ventricle empties, it goes all the way down. And then it fills up again. And here you see the valves, so they open or closed, both valves. And then here you've got the visual, where's the blood going. This is a very good chart. It gets you very far in understanding this vascular dynamic stuff. And look at that, that's the last line. Wow. Finally. You must be asleep by now. So we then have to measure how much blood do we pump each minute. And we said the stroke volume is how much we pump per minute, how much we pump per pumping time, per strike, per contraction. And that's about 70 milliliters at rest. That can double. You go, how that deep? Well, if the heart pump's stronger, it can be stretched a little bit more too. And so that's the double. And then the other thing we need to figure out how much blood is pumped per minute, we need to know how many times we're pumping that thing in a minute. And that's the heart rate. And that's at rest about 70 beats a minute, more or less. And so then we can calculate. Look at that. We can go 70 times 70 is 4,900. 4,900 milliliters per minute. I know it's science. You got to do milliliters, deciliters, liters, all that kind of stuff. Milliliter, I don't know the equivalent of a milliliter. But I know that's about 5 liters. And the quart, I mean, a gallon is about 3.6 liters. So that's a lot of blood. And look at that. The cool thing is, you can, at maximal exertion, you can go from 70 beats to about 180 beats a minute. Although, when you look at maximum heart rate, you do 220 minus your age. So 180 is about 30 years old person. And so I mean, those are all sort of ballpark figures. But if we do that, look at that, that's about 25 liters in a minute. That's 5 times. The heart can pump 5 times its resting quantity if it needs to do that for brief moments. So that's what you do when you need to run away from a lion or something. But it's pretty good. Yeah, well, that's a full-fledged sympathetic overtake. I know, I mean, maybe you freeze, right? Anyway, so that's what I have for this situation here.